Okay, so today we're going to walk through the solution to the problems I assigned for homework 5. The PDF of these solutions is available online, and I'm just going to project that onto the screen. So this is the same document that's in Blackboard, and you can follow along just on the screen here in the video, or pull it up in your other window, or whatever you want to do. So the first problem I assigned was problem 7.1 from the textbook. This was one to just think about how the density of the air changes under different conditions and how that affects the power production of a wind turbine. So we have a horizontal wind turbine, 20-meter diameter rotor, 30% efficient, 10 meter per second winds, standard conditions. So how much power will it produce? Well, we just go to the power equation for the power carried in the wind, 1/2 rho AV cubed, and then multiply that times the efficiency. Plug in the standard sea level value for the density of air, 1.225 kilograms per cubic meter, and we get 57.7 kilowatts. So about a 60 kilowatt turbine, which by the way is unusual. That's a smallish turbine. It's too big to be something you put in your backyard, but it's not big enough that you'd use on a utility scale wind farm. So I'm not sure whether the author had a particular turbine in mind. This does not ring a bell with me at all. Part B was, okay, let's say we put this turbine at 2,500 meters elevation, which is pretty high, right? That's, that's 6,000 feet, maybe 7,000 feet, so that's a high elevation. And it's cold, or colder, 10 degrees C. And this is just to kind of get you a little used to this equation that accounts for both elevation and temperature and predicts air density. So it's a 7.17. And like a lot of these things in this section, this is an empiricism. It's a curve fit that they've kind of put together from first principles of thermodynamics and ideal gas law, and also probably some measurements as well. So Z is the elevation in meters, T is in Kelvin. So 10 degrees C is 283.15 Kelvin, because you have to offset that. And that gives you a rho of 0.92. Now compare that to 1.2, and you see that's a pretty big difference, right? And then the final question, what's the power under those conditions? So, you go right back to that original equation, part A. Let me scroll up. This one here, density, zeta, 1/2 rho AV cubed. Redo it with just a lower rho. What I did was I just got lazy. I took it to 57.7 divided by 1.225 multiplied times 0.9223. And you get, not surprisingly, a lower value. So a 57 kilowatt turbine really is derated down to 43. So pretty significant cutback. So that was the first problem. Everybody did well on that. That wasn't a big surprise. Problem 2, problem 7.3 in the book. Just looking at a slightly different situation, tidal energy. So what I like about this, it shows that tidal energy isn't really different from wind energy. You have a different flow regime. You probably don't have Weibull distributed statistics or Rayleigh winds or something like that. But the equations are all the same. In fact, you don't really need to worry about statistical distribution because the currents are quite predictable and quite constant. So what do we say? We have a sinusoidal max flow of 2 meters per second, and they did some math for you. So if they specify the max flow of a sinusoidal flow regime, they calculated the V cubed, the average of the cube of the velocity, not the cube of the average velocity, as 4/3 pi times the maximum velocity cubed. So we're given that of 2 meters per second. So from there, it's pretty easy to just go into our equation about for power, for the average power, and we want to know power per unit area, so you pull the area over to the other side and end up with this fairly simple equation, rho/2, 4/3 pi times the max velocity cubed. Pretty simple algebra to get to there. And the answer is 1.7 kilowatts per square meter. So let's make sure we know what we're looking at there. That's the power density of the flow regime. We haven't even talked about a turbine. We haven't specified a turbine. We haven't talked about how to extract that energy. That's just the energy that's available there, right? So now you put a 20-meter diameter turbine in there. It's rated at 600 kilowatts. Has efficiency of 30%. I had a lot of questions in this that showed people were getting a little confused. on what we're looking at. So again, that 1.7 kilowatts per square meter is an energy density. It's got nothing to do with what we're producing. Now we put something in the water. We specify size. It's 20 meters diameter, pretty big, but it has an efficiency of 30%. So how many kilowatt hours per year would you expect it to deliver? So we start with that average power density we talked about, and now put in the rotor area, because that 1.7 kilowatts is per square meter, multiplied times the area, the disk that it presents. So that's pi r squared. There's pi times 10 squared. Then times the efficiency, and that's the power, the average power level coming out, and that's the power available of 160 kilowatts. So that would make sense. You've got a 600 kilowatt turbine, but on average you're not going to get 600 kilowatts. You get considerably less. Multiply that by 8,760, you get 1.4 million kilowatt hours per year out of that turbine. And this just kind of, one of the things that's interesting is that 600 kilowatt rated power was never used. We didn't need it. It was sort of one of those little extra tidbits they threw in there. I was curious to see, well, where does the rated speed of this turbine fit into the flow regime? So we're fluctuating from 0 meters per second to 2 meters per second. So I went back to the original power equation and said, well, it's rated at 600 kilowatts. There's the density, 1/2 rho A, and then V cubed. So whatever V makes that work is the rated speed. So another way to look at it is, what's the rated speed of this? And it's 2.33 meters per second. So the turbine is kind of oversized for this flow regime. That's one way to look at it. If it never gets above 2 meters per second, you probably don't need a turbine that's rated at 2.33 meters per second. On the other hand, if that's what's available, may not be a bad pick. You're going to use a machine that's somewhat underrated. Maybe it'll last longer. Maybe it'll hold up a little better. Okay, problem 3. 82 meter diameter rotor on a 1.65 megawatt turbine. Now this is one of the big ones, right? This is the turbines you see across southern Idaho. I think I mentioned this in class. They range from about 1.5 megawatts to probably about 2.5 megawatts. So this is on the small size of the turbines we're seeing in our state. It's got a rated speed of 13 meters per second. So if the turbine says it's rated at 1.65 meters per second at a rated speed of 13 meters per second, that's telling you where the knee in the power curve is, where it starts flattening out. And it also tells you that at 13 meters per second, it's going to produce 1.65 megawatts. So what's the rotor tip speed? Oh, they said the rotor tip speed ratio is 4.5. So what is the speed of the rotor itself? How fast is it spinning in those 13 meter per second winds? Well, the tip speed ratio is just what it sounds like. It's the ratio of the velocity of the tip of the blade to the wind velocity, and it's greater than 1. So omega r is the linear velocity of the tip of the blade. We've got everything there except for omega. We solve for omega, and it's 1.52 radians per second. Do a little unit transformation. It's about 14.5 RPM, and that means it's 1 revolution every about 4 seconds. So next time you drive by there, or hopefully somebody else is driving along I-84 and look at the turbines, you kind of get a sense. Count how long, maybe even get a stopwatch or something, see how long it takes for it to do 1 revolution. And if you can count, if you're pretty good at counting, 1 second, 1/100, 2/100, or something like that, you'll see that you get about 1 blade per second. So it's in the 3 to 4 seconds per rev range. Okay, so what is this velocity? What's the linear velocity of the tip of that blade? And I don't know about you, but I was kind of surprised when I did the math on this. I mean, I knew these are big machines we see from a distance, so it's kind of hard to judge speed, but I would have never guessed that the tip was actually going well over 100 miles an hour. So right around 140 miles an hour is how fast the tip of those rotors are running at this tip speed ratio. Tip speed ratio in kind of its sweet spot where it's getting the most energy is probably closer to 6 or 7. So this is on the low side. Part C, real straightforward. The rotors turn 14.5 RPM. The generator's got to turn at 1800 RPM. Just do the math, 124 to 1. And again, the point of this problem isn't to test your ability to do analysis is to drive home what these machines do. So that gearbox has over 100-to-1 gear ratio. And think back of, ME380 or these classes where you dealt with gear trains. A car's gear ratio is like 4-to-1 or 5-to-1, depending on what gear you're in, the transmission in your automobile. So this is a significantly bigger engineering challenge than, say, an automobile transmission, not to mention huge power levels as well. And then what's the efficiency? Well, that gets back to this issue that at rated wind speed, 13 meters per second, we know it's generating 1.65 megawatts. So the question is, what's the input? What's the energy of the wind at that speed? And we just use the trusty 1/2 A rho V cubed. V is 13, and we get an efficiency of 23.2%. So, and that's satisfying. That's pretty typical for wind turbines. Keep in mind the Betz limit. The Betz limit would apply to this calculation. So if you do this kind of calculation, you end up with something over 59%. You've got a mistake somewhere because it can't be any higher than that. Okay, moving right along. Problem 4. This is 7.7 in the text, and this was about the wind resource characterization and how we use statistics to represent it in a more compact fashion rather than big spreadsheets or an entire annual wind record. We can bin up the wind speeds and averages and get a sense of how those are distributed, and if they look like this Rayleigh distribution, then we've got a series of equations we can apply to it to make it a little bit easier. So this particular turbine, and I think I don't have the problem in front of me, but I think we refer to a column in the table of the text. Cut-in speed's 5 meters per second. It furls at 25 meters per second. That means at that speed it's going to stop generating. Furling is referring to that process where the wind blows the turbine blade out of the wind, the rotor out of the wind so it doesn't capture the wind. It protects it from real high wind speeds. And the region we're in is an average wind speed of 9 meters per second and also specifies its Rayleigh distribution. So several sub-questions here. First one, how many hours a year can you expect the turbine to be furled? So how often is that wind blowing so high that we're not going to capture any of it because frankly it's scary. It's going to damage the turbine too much. And this is what the probability density function, particularly the cumulative density function, is very good at. So I forgot what the equation number was, but it's in the book in this region. And it says the probability that the wind at any given time would be greater than some speed, capital V, is given by this, the exponential of minus pi over 4 times the ratio of that speed to the average speed, square it. So in this case, capital V is 25 meters per second. The average is 9. Go through the math, you get a 0.00233. So that's the cumulative power. It's kind of, if you think of the probability density function as, it's not the Gaussian symmetric one, it's skewed. But this is the area, that tail of the curve at the higher end from 25 out to infinity. That's one way to think about this. And it's small. It is a small chunk of the tail. And to figure out how many hours that is, you just multiply that times 8,760, so it's 20.4 hours it spends that. So over the course of a year, it's less than a day it spends out of service. I guarantee you, particularly for a newer turbine, it's going to spend a lot more than a day out of service when you're messing around with it, trying to get it up and running and get everything dialed in the way we want it. So the similar question asks the other end of it, is how many hours can we expect it to not be operating because the wind's too low? So what's the probability the velocity of the wind is less than, in this case, 5 meters per second, which is the cut-in speed. And it's important to note these cumulative density functions. There's two versions of it, right? One is the right end of the tail, one is the left end of the tail. So this is the left hand. So what's the probability of velocity? It's less than, not greater than, a given value. So this is the lower end of the tail from 5, in this case, to 0. And since the area under the entire cumulative or probability density function has to be 1, then this other equation here of the v less than or equal to v is 1 minus e to the minus pi over 4 times the ratio squared pretty straightforward. This one is a bigger chunk, this tail. Again, this is a skewed distribution, so the lower tail is a little chunkier. It doesn't have that long, narrow tail like we had on the high end, and not surprisingly, 0.215, a bigger one. So close to a quarter of the time. That's what that's saying, which multiply that times 8760, not surprising, 1,886 hours per year of very low wind. So the third question is, how much energy can we expect from the turbine at between 12 and 25 meters per second? And if you look at the table, that's the rated power. The power is the same at every one of those values of wind. And so we want to know, what is it between 12 and 25? Well, we know what it is greater than 25. We know that's only about 20 hours, 20.4 hours. So if we know what it is greater than 12, which is, from 12 to infinity, and just subtract off the hours is greater than 25, we've got our window. So sure enough, you take the probability of V greater than or equal to 12. It's about 2.5, about a quarter of the time. A little bit more than what it is, under 5. You get 2167 hours per year. You subtract off the 20 hours that it's too fast to capture any energy. You get 2147 hours per year. Multiply that times the rated speed, which I believe was 1 megawatt, and you get 2.15 times 10 to the 6th, or 2.15 million kilowatt hours of energy. So again, none of this is real rocket science, but it's it's important to help you keep track of the units, figure out what you're doing. And finally, problem 710, the fifth problem in this homework, was getting to use the capacity factor empiricism, the little curve fit that the author presents. I have not seen this in any other reference, in any other book I've seen. But the fact that it has survived to the second edition of the book tells me, yeah, it's worth covering. I didn't cover it last time I taught the class, but he had more data behind it in this book and this edition, and I think I'm comfortable with it. And it's a really simple little equation. It helps you predict the capacity factor of a turbine in a given wind regime. This is, of course, assuming Rayleigh winds. The V bar is average wind speed. PR is the rated power in kilowatts. And again, I mentioned this in class several times, mentioned again, these empiricisms, these curve fits, units are important. You got to make sure you get the units right, because you've got this coefficient that was fit to the data in specific units. So powers in kilowatts, diameter of the rotors in meters. And they say, okay, you've got an average wind regime of 5.7 meters per second, which, by the way, is considered kind of light. Okay, that's not going to be a really strong site for a wind farm. And they say there's two versions of this turbine, one at 2300 kilowatts, 2.3 meg, one's at 3 meg. So which one of these would be the better choice for this wind regime? And it's a two-step process. Find the capacity factors we could expect from the two turbines, and how much energy they'd produce. So not surprisingly, if you think this out, shouldn't be surprising, the bigger generator had a smaller capacity factor. Same amount of energy is available to the two turbines, but since this has a bigger, in this case, denominator, if you think of how a capacity factor is calculated, you'd expect it to be lower. And so you multiply that times the rated power times 8760, and what you get is a little surprising, at least to me, was that the smaller generator made better use of that wind. We were able to get more wind out of it, 4.55 times 10 to the 6th kilowatt hours as opposed to 5.44 million versus 5.3 million kilowatt hours. So the smaller generator was the right choice, and of course the fact that you're undoubtedly paying less for the smaller generator just makes it doubly good, and also drives home the fact that matching the right turbine to a given wind site is very important. You can't just keep putting the same turbine up at every site because there's only going to be one or two designs that's really the best design for that site. What is the best design for this site? What's the best generator size, at least? Well, you can find that out. So the book walks through this derivation. I thought I'd do it here just because it was kind of fun to do. You combine the two steps we did in the previous part A. Find the capacity factor, use the capacity factor to find energy. Put this together, in symbolic form. So instead of plugging the numbers, keep the symbols together. So you get this equation here where the energy you'd expect from the wind farm in a year is equal to hours in a year, 8760, times P, times, of course, this is the capacity factor, 0.087 times the average velocity, PR divided by D squared. Put in the numbers for this problem. The D is, I forgot how big, 101. The V bar is 5.9. Anyway, you get this quadratic for the E, for the energy in a year. So we want to find what's the P that maximizes the E. Take the derivative of E with respect to P, set it to 0. So simple derivative calculation. Solve for a P, we get a P of 2529, somewhere between that 2300 kilowatts and the 2300 kilowatts, 3000 kilowatts, right in the middle. We find that through and find, sure enough, we'll get a capacity factor of about 2.5, total energy of about 5.5 times 10 to the 6th. And you know, if this was optimum, it should have produced more energy than any of the other two choices, and indeed it did. So good for us. One last question. Since you know, the smaller generators do best in a lower wind regime, that would make sense to take to the next step and say, well, a bigger generator will do better in a higher wind regime. So this part of the problem, this last thing we worked on, said, what's the wind speed? What's that crossover? What's that wind speed where the better generator, as you go into higher and higher wind regimes, what is it that the bigger generator, when do you get the better results from the bigger generator? Again, find the energy produced from each one of them. Just put in an equation. Keep the V bar as a variable now. And that crossover point is the wind speed at which the two generators will produce the same amount of electricity. So you just set them equal to each other and do the math. Pretty easy. Nearly everybody got this right. Just under 6 meters per second is the answer here. So that's it. It's been about 20 minutes. It's kind of a long video, but I wanted to just kind of get it all done. So yeah, that's it. Any questions? Make sure you let me know. Thanks.